Okay, so here's where we were last time. We were leading up to the definition of something called an inner product space. We didn't really quite have time to get there, so let me just remind you what we'd been talking about. So very first thing I suppose I should do is remind you about what we did when we were thinking about Rn and how to generalize that. So we talked about, it was a silly exercise that we did where we said, well, let's write down a theorem. Let's write down a theorem in Rn about taking linear combinations of vectors and state and prove the theorem. And then, instead, consider a situation where we're taking linear combinations of functions. And we know that that's the exact same, it's morally equivalent algebra, the same. We really have to do this proof all over again. Well, technically we do, because we were narrow-minded enough to only state and prove our initial theorem in Rn specifically, right? So this repeated a couple times, and we started to see the preposterousness of this and decided to avoid the problem by defining something called an abstraction. And so here was the big idea there. We're going to define this thing that's called an abstraction, this vector space, what it ended up being. Right? And the idea was, I don't want to tell you what my objects are. I don't want to say these are specifically vectors in Rn, or these are specifically, functions in some, collection of space of functions. I want to say, look, these could be whatever. Let's not even talk about that. I don't know what they are. I just want to tell you, what kind of properties do they satisfy? Like, I can add them. Whatever that means. I'm going to be very ambiguous about what addition means, but I need addition to behave a certain way. They have certain algebraic properties. And then, when we get to talking about theorems, we don't state the theorem in the narrow-minded context of, Rn or something like that. We state it in the abstract. We prove it in the abstract. And then we don't just have one theorem, now we have a bazillion theorems. Right? We have a theorem that is true in Rn, because Rn is a vector space. It's true in C0, because C0 is a vector space. And it's also true in any other vector space that you might eventually encounter, maybe something you haven't even thought of yet. And in fact, that happened to us as well. We found that by stating and proving theorems about vector spaces, we ended up being able to do neat things with differential equations. After all, solutions to a linear homogeneous differential equation are always vector spaces. Okay. All right. So we're going to repeat that strategy now. Again, we're going to be thinking about Rn, but unlike in the context of vector spaces, we were looking at Rn, vector addition, and scalar vector multiplication, which, nobody writes with the times, but I'm going to do it that way anyway for reasons that you'll see in just a moment. So we were thinking about, look, we've got a lot of experience with vectors in Rn that we can add and multiply by scalars. Anything that behaves kind of like this, we're going to call a vector space. And by kind of like this, of course, we wrote down a bunch of properties here. Right? Remember this page, it has this long list of properties. So a vector space is anything, a set, an addition, a scalar multiplication, and then all 8 of these properties have to be satisfied. Okay, what we're going to do now is we're just going to add one thing to the list. We're going to say now, comma, dot. For the dot product. We're going to think now about this quadruple. Okay? It's not just the set of vectors with an addition and a scalar multiplication. Now it's all of that, but then also this dot product. Now Rn, we have a lot of experience working in Rn where we were doing things like adding vectors and multiplying by scalars and doing dot products. A lot of what y'all did in Math 212, after all, involved dot products in Rn. Right? So, well, golly, the dot product was super valuable in Math 212. Maybe generalizing on this concept would lead to useful things. And it's going to turn out that it does. It leads to some extremely powerful results. So anyway, that's the big idea. We're leading up to a definition of something called an inner product space. And it's, like I say, just kind of what we're leading up to here. It's a vector space, namely, it behaves like Rn with addition and scalar multiplication, so vector space. And we're just going to add in one additional operation that behaves, morally, kind of like, in some sense that will make precise, the dot product. Okay. All right, so let's look down at the properties of the dot product that we already know. Here's a long list of properties of the dot product. Here are some properties that the dot product satisfies. Here's some more. Here's still more. You may be wondering why I have these labeled in 3 separate groups, and there's a reason for that. So for the moment, I'm going to sweep that under the rug. And I'm not going to go through all these properties. All of this is old news. You should already know all of this stuff. So look it through and make sure that you remember all of these facts about the dot product. Okay. What we're going to do is use these first 4 and say, look, any product-like operation that we can define on vectors that satisfies properties like these, we're going to say that's kind of like the dot product. So you'll notice here on the next page then, this is our definition. We want to start with a vector space. Well, of course, we need to have the vector addition. We need to have that scalar vector multiplication. We're supplementing that then with an additional operation. This is going to be our dot product-like thing, our new operation on vectors. Apologize for the notation. It's a weird notation to put the vectors inside of triangular brackets separated by a comma. Anyway, this is how it gets written. So anyway, it's strange. But that function just needs to have those same 4 properties from the previous page. Any operation that you can define on vectors that satisfies these 4 properties, we call an inner product. And then this combination of vector space with an inner product, we call an inner product space. So we go into this with a lot of optimism of, hey, abstractions, generalizations sure did work out well for us when we were playing around with vector spaces. So maybe we'll get just as lucky here. Okay. Before I go on, does anybody have any questions? Everybody good so far? Okay. Right. So let's see some examples before I get to some other things. The first one is silly. Rn using the dot product is an inner product space. I hope this is no surprise. Let me say this in a different way that'll illustrate, I think, why this is a silly example. Remember, being an inner product space means that it behaves kind of like Rn using the dot product. So, question, Rn with the dot product, does that behave like Rn with the dot product? Well, yes, it does. It behaves just like itself. Right. So, silly observation. But, if you want to, for completeness, you want to go through and confirm that all 4 properties are satisfied. Very good. Okay. All right. Now, this next example, not obvious. In fact, this is kind of deep, really. There's tremendous consequences of this next example. Very, very important. So here it is. Here's the vector space that I want to talk about. C. Y'all remember C. This is the vector space of all continuous functions. That they only have to be defined on this closed interval from A to B. Right? Continuous functions defined on this closed interval from A to B. Nevertheless, that's a vector space. You can add any 2 continuous functions, right? You can multiply any continuous function by a scalar. It all works. Okay. The additional operation that we're going to use is this really odd looking at a glance formula. If you give me any two continuous functions, f and g, inside of this vector space, I'm going to compute a real value as follows. Namely, I'm going to take these two functions, I'm going to multiply them to get a product function, then I'm going to do an integral of that product. And that's the formula. So this is an inner product. So this satisfies these four properties up here. This is an important inner product. Let me go back down here. So this is called the L2 inner product. We're not positioned for me to be able to tell you where that name comes from. There's a very natural reason to call this the L2 inner product. But anyway, so y'all just need to know that name, and you don't need to know the context. Okay, pause for questions. Okay. I want y'all to prove that this is, in fact, an inner product. This is not so hard to do. Again, all you have to do is prove these four properties. The first three of these properties are very straightforward. It's very kind of plug and chug. So definitely do those. Look at those first three properties. Show that this formula does those things. Ultimately, proving that this satisfies those first three properties is a matter of writing down, translating those properties into calculus and just reminding yourself that you know basic facts about integrals from Calc 2, Calc 1 maybe even. All right. Heads up, though, this fourth property is trickier. This is not just a matter of writing down basic properties of integrals from Calc 1. You have to really think that one through carefully. Specifically, you're going to have to use the continuity, the fact that these functions are continuous. And it's still, a clever, tricky argument. So give that a try, property number 4. Give it a try. And if you get stuck, it'd be a great question for office hours or discussion section or, reminder, TA office hours. You're also invited to those as well. Okay. All right. Before I go on, I want to call your attention to another thing. The book doesn't write this definition down the same that I do. The book writes those three properties down the same way I do, but the book writes this one down differently. Number 4. The book does not specifically require that a self-inner product be non-negative. The book's version of what I'm going to call property number 4 is just that a self-inner product can only be 0 if the vector is the 0 vector. So that's not just a different phrasing, that is actually a different property. Right? So the book's definition is a different definition. I also think the book's definition is a problem. It leads to something bad's going to happen if we were to go with the book's definition. So I'm making this change. So for the purposes of Math 216, this is the definition right here. And ignore the book's definition. It's not the same, and it's really not okay. All right. Let's see here. Moving along. Yeah. So here's another one. Here's an easy fact to demonstrate. The way I say this in language is dot products are not preserved by change of basis. I think this is pretty believable. If you take a dot product of the standard coordinates of a vector, you get some value. Well, if you look instead at coordinates with respect to another basis, you get totally different coordinates. Of course, you're going to get a different value. Right? And so highly expected that this dot product also would be different. So no surprise with these being not equal. So that being said, now we already know that dot product is an inner product. That's easy. Again, that was our model. Right? This, dot product in a different coordinate system
is not the same, but it turns out it is still an inner product. It's just a different inner product on Rn. So it's, kind of a neat observation. There are reasons sometimes to want to do this. We'd have to go pretty far into the weeds to show you an example of that. But sometimes looking at dot products and other coordinates, convenient thing to be able to do. Okay. All right. So this thing is an inner product. Exercise 9, I just want to point out to y'all, effectively asks you to prove this. It's just a matter of going up and checking these 4 properties. Just, got to go through them one at a time. Just do them. Exercise 9 doesn't phrase it this way. Exercise 9 phrases this differently, but it's a nice sort of supplemental exercise to look at what exercise 9 actually asks you to do, and then look back at this, and then make the connection and realize that these are, in fact, ultimately the same question. Right? So, anyway, this is just something to be thinking about as you're doing exercise 9. Okay. All right. So let's go back, having seen some examples now. We've taken our dot product in Rn. We've defined what we mean by stuff that behaves kind of like that, right? Something that behaves like Rn in the sense of addition and scalar multiplication, but which also behaves like Rn in terms of there being a kind of a dot product-like construction. We used only these 4 properties as our model. The dot product, however, has all of these other properties. Why didn't we use these too? Why didn't I require, for example, let's look at this next collection here. Why didn't I require these? Seems like we ought to. I mean, after all, the dot product behaves like this. If I want something to behave like the dot product, well, doesn't that mean shouldn't I have to have it satisfy these properties too? Shouldn't that therefore be part of the definition? It's a very reasonable gripe. Here's the good news. I don't have to, because it's free. These initial 4 properties automatically imply these 3 properties. They come along without having to prove them, right? So I'm going to leave these as exercises for y'all as well, but these 4 properties, if you assume that your operation does this, try to prove that they also do this, and it's automatic. Right? So for example, notice this one here. So let's look at the second one. How do I know that this is true? How do I know that anything that satisfies the green properties up there must satisfy this blue property down here? Well, this formula that I have, V dot U plus W, by the first property up there, I can switch the order. Then by the second property, well, I can distribute by the second property with the sum being on the left, and then I can switch the order back again by property 1, and this follows immediately. Okay. So let me color code here. These make up the definition. These, what I call more facts, are free. Which is convenient. So, look, if you wanted to, if you're just, glutton for punishment, if you want to add these to your definition, go ahead, you can. If you want to check them every single time, okay, right? But they're always going to work if you've already checked these first 4, these are going to work every time, and you're just doing make work. There's no point. Okay. All right. Now I want to add to that list of more properties. The book doesn't mention these, but I think these are important. Here's another property that inner products all have. The dot product has this property as well, but more to the point, all inner products. They are linear in each entry. Let me tell you what I mean by linear in each entry. What I mean is, if you think of inner product with W as being a function, if you think of inner product with W as being a function, that function is linear. Now, what do I mean by linear? Well, remember, linear means that when you put a linear combination in, there's a linear combination going into what I've, this odd notation function that I've described here. Inner product with W is my function. So you put a linear combination in, and notice you get a linear combination out. That is the definition of linearity. Right? So you can think of this formula here as being a great big massive beast. Or, I think more conveniently, inner products are linear in each entry. Okay, so what we have here is linearity in the left entry, and linearity in the right entry would mean if you view this as being the function. And then again, notice linear combination in, linear combination out. So that's linearity in the right entry. How we doing? Questions? Everybody happy? It's kind of you might call this a super distributivity or something. Kind of. Okay. Alrighty. So let's go back now to this first page. We've got that first collection of green properties up there that make our definition of an inner product. This second group of blue properties come along for free. We don't have to check them. They're automatic. This is sweet. So, hey, what about these still more facts down here? Are these automatic? Do these just jump in the boat as well? Wouldn't that be nice if we had more free stuff? Sadly, no. These are not automatic. So why don't I make them part of the definition? You might reasonably ask, right? If I want to define something called an inner product, maybe I'd better check that the inner product behaves like the dot product in the sense that, if you compute like we have here, that maybe you'd better get angle, and maybe, better check that when you do a self-inner product and take the square root, that you get the magnitude. Why don't we require that if we want this thing to behave like the dot product? And the answer is, it doesn't make any sense. I can't check if an inner product connects as it should to length in a context where I have no notion of length. Right? That's the problem. There is no pre-existing notion of length or angle in these other inner product spaces. Now in Rn there is. In Rn, length means distance. Pythagorean rules and all that. Right? So I could ask, does the dot product connect to length as it should? Yes, it does. But now here's a ridiculous question. Let's suppose I'm thinking about the inner product space of functions. What is the angle between two functions? Right? I don't know what you're talking about. Right? Initially, at a glance, we just don't have no pre-existing idea. So you can't require that something's true if your requirement isn't well defined yet. So that's too bad. So what are we going to do instead with these? And this is another bit of good news. We're going to use these to make definitions. Those property are going to give us definitions of magnitude and angle. Okay, so let me show you explicitly what I mean by that. We're going to take this property here. Magnitude in Rn is the square root of the self-dot product. Likewise, magnitude in an inner product space is the square root of the self inner product. Well, it's just a total ripoff, right? Very natural. It's kind of following along and saying, look, let's just try to reproduce things as much like Rn as we possibly can. So this is our resulting definition of magnitude of a vector in an inner product space. Okay. All right. Lingo thing. Sometimes these are called norms. So norm or magnitude. You might even hear people refer to this as the length of a vector in an inner product space, and sure, I suppose that's fine. Okay, seem like a reasonable choice? Anybody questions? Feel free. Okay. All right. So, for example, don't forget we have the L2 inner product on C0, right? The vector space of continuous functions. Attach this inner product. Now we have the inner product space of continuous functions. And using this formula, this definition, what's the magnitude of a function? Well, the magnitude of a function is the square root of the self inner product, so therefore that. It's a very weird little formula. The square root of the integral of the square of the function in question. All right. So now this is again just a kind of a semantical thing. This is called the L2 norm. Norm because it's a norm. L2 because it comes from the L2 inner product. So pretty reasonable choice of terminology, I think. It's just a formula. Okay. All right. How we doing? Everybody okay? That's a definition. Analogously, we can make a definition of angle. Let's go over here back to our starting page. How do we define angle? Well, I'm going to define angle like this. If you give me any inner product, I'm going to define the angle between two vectors in that inner product space as the arc cosine, weird, of the ratio of the inner product to the product of the magnitudes of those vectors. Only because, well, this is how it works in Rn, and I would like my new algebra to look just as much like Rn as possible, so therefore I'm going to make this choice. All right. So let's see an example of that. Here it is. Here's that formula, by the way, the angle between two vectors. Is that? And I'm going to punch one up just to get our hands dirty, see what this looks like. So let's find the angle, theta, between these two vectors, sine x, which is going to go there, and cosine x. Sorry, I was thinking about something else. Sine of x plus phi. So there I have two vectors in C0, a known inner product space. The angle is defined as that arc cosine, and plug and chug. It's a little tedious. Apologies for the tedium. It is what it is. But these magnitudes are just a matter of computing them, right? That magnitude, compute that integral. Now, I just glossed over some inconvenience, and make sure that y'all can do this. The integral from 0 to 2 pi of sine squared, non-trivial to do that integral, right? Make sure you remember how to do that. I know it was a while ago, right? Calc 2, think way back to Calc 2, and make sure you can get this answer. Y'all think you can do that? I know it's been a while. By the way, now this is a good opportunity for me to throw in a historical note about this course. We have actually been asked by the Pratt School, a vast majority of y'all at Pratt. Those of you who are not, when in Rome, right? But Pratt has actually asked us to make sure that we keep y'all nicely honed on your single variable calculus skills. Right? So some years ago, this was a long time, it was probably 20 years ago at this point, Pratt came to us and said, hey, we don't know how this could be, but we have, junior and senior engineering majors
who can't do basic integration anymore. What's going on? And what we figured out was that there were a fair amount of instructors who were teaching Pratt math classes like 216, 212, 216, 353, who were just kind of leaving on, don't worry about the integrals, I know y'all how to do that. Right? And then so, in some sense, y'all got so much trust, y'all were probably not even alive at that time. But those Pratt students were getting so much trust that they didn't have to do any integrals for years and years, and it was catastrophic, right? It's simply not okay as an engineer to not be able to do some basic integrals, right? So make sure you can do this. On exams in this class, stuff like this you're going to have to be able to crank through and figure out values of standard integrals like this one. By the way, in case you are sufficiently rusty that you don't remember how to do this one, half-angle formulas. Half-angle formulas are your friend. Okay, next step, we've got to compute this integral. That magnitude, which is that integral, and it's morally equivalent, so make sure you can do that one as well. Then finally, we've got to compute this inner product, which is itself also an integral. And this integral, it's a little bit different. Keep in mind that in this little story here, phi is a constant. It's not a function of x, right? So since that's a constant, that makes these constants, and those constants factor out of their respective terms, thus giving you simply these two integrals left to compute, and those are quite doable. Again, make sure that you can do them, and punchline is that. Okay, so a lot of tedium, but the punchline is we just computed those two magnitudes, we just computed that inner product, and therefore the angle between these two vectors is that phase shift phi. So I call this good news here. I like this as an answer because I find this very intuitively satisfying. Let me point out why this is satisfying. Let's look at what we're talking about here. These two functions. Let me draw a picture of them. There's 0. There's 2 pi. Let's draw sine x. Let's draw sine of x plus phi. Okay, so sine of x plus phi. It's shift. Oh, I didn't finish sorry. So it's just phase shifted to the left a little bit. So let's think through some cases. Okay, what happens if phi is small? If phi is a small number, what should be the angle? I mean, thinking of these two functions, forget about phase shift. Thinking of these two functions as being vectors in some, vector space. This infinite dimensional vector space of all continuous functions. If I'm thinking of those as vectors, how would I compute the angle between those two? What should the angle between these two vectors be? Well, gosh, I can't visualize this vector space. Inner product space. It's infinite dimensional. I'm really not capable of doing that. But look, these functions kind of track each other. The values of the green function, the values of the orange function, they're pretty close. And so now I appeal that infinite dimensional though this inner product space is, if you have two vectors that are pretty close to each other, if they're not that far apart, then the angle between them should also be small. Doesn't that seem pretty satisfying? Right? If two things are close, their angle is small. So what we have then is that in the case that the phase shift is small, the angle, the inner product space angle between them checks out as it should be also small. And you can think about other cases. Think about what happens. Oh, a really nice one is to think about what happens. Let me go ahead and do this one for you. What happens if if phi is pi? If phi is pi.
Well, let's see here then. If phi is pi, it shifts over at a half of a period, and you get that. That's what happens when you shift over half of a period. And notice that these two functions, they're not a lot alike anymore. The values are not equal or nearly equal. What they are, however, is exact negatives of each other. And now, so these, seeing on their graphs that these two functions are now exact negatives of each other, what would that look like in an inner product space? It's not going to be like this anymore. But exact negatives of each other will be like this. Well, these two vectors, exact negatives of each other, what do you feel like should be the angle between two vectors that are exact negatives of each other? Well, that ought to be pi. Right? So, again, it tracks, right? I mean, when phi is pi, when the phase shift is pi, the inner product space angle, as it should be, checks out as pi. Okay. So, anyway, so like I say, I call this good news. I think this is an intuitively satisfying result. And good for intuition. Everybody good? Yeah. Mm-hmm.
Well, how can we do the functions of polynomials?
Yeah, right. So, I mean, it's going to be hard to visualize. Like, it's hard to make intuitive arguments like this about, what should be the, like, if you give me a random polynomial, another random polynomial, right? I mean, you can do a calculation, you can compute what that inner product space angle is, and it is what it is, but I'm not going to be able to compare that to intuition because I don't really have a good intuition for what, I mean, if they're two random polynomials. So, but the formulas are all analogous. Anybody else? All right. Okay. Here's another fact. Cauchy-Schwarz inequality. Y'all probably remember the Cauchy-Schwarz inequality from Math 212. Actually, those of you who took Math 212 with me may have a memory that at the time I pointed out that even though this property of the dot product is kind of not as powerful as magnitude times the cosine of the angle is much better. That's the one that seems to tell you the most information about the dot product. So why is this one the one that gets the name? All right? Why do we get a name for the Cauchy-Schwarz inequality? And the answer is that this does not rely on your geometric notion of angle. And this, furthermore, completely independent of any geometric pre-notion of angle, this is true for any inner product space. This is not a peculiarity of Rn. Right? This is always true for any inner product, which is weird. And you can, the proof, I mean, the proof's in the book. You can take a look at that if you like. It's not something you're responsible for. But let me just show you how unexpected this, pretty basic fact about inner products, how unexpected of results you can get out of this. And I'm just going to apply this to the L2 inner product. Let me remind you, the L2 inner product. Here it is. There's our L2 inner product. Let's see, what does the Cauchy-Schwarz inequality look like with the L2 inner product? Okay, absolute value of the integral from a to b of f of x times g of x dx, right? Absolute value, that's what this is in the L2 inner product, is always less than or equal to, well, let's see here, the magnitude of that first function. The magnitude of the first function is the square root. Okay, I'm already kind of weirded out by this. Integral from a to b of f of x squared dx, and now times the square root, that being this next magnitude that we're looking at, of integral from a to b of g of x squared dx. So this crazy looking identity, right? This is true for any two continuous functions. Think, how would you in the world would you even begin to dream about proving this in a Calc 2 class?
I don't know any Calc 2 integral properties that would even let me get a foot in the door on proving this. But it's an immediate result of the Cauchy-Schwarz. Weird. Okay. So, moving along. I want to show y'all an example that involves statistics. I know a lot of y'all haven't had a statistics class yet, and that's fine. If you have not had a statistics class, I strongly encourage you to think about the following point of view that I'm about to give you when you do take a stat class. If you haven't had a stat class, see if some of this if you've got this geometric point of view on statistics from that class. If you didn't, you might find this really, really interesting. I think this is just phenomenal. So here's the idea. There's this formula called covariance. It's a formula. It's something. Here it is, right? So an expectation value is an integral that's computed of a certain expression over the sample space for the random variables. It's just think of it as a great big integral. Okay. And when you have random variables, let's say x and y, a couple of random variables, like maybe I've got a bucket of rocks. Mass is a random variable because each one of those rocks has a mass, right? Then volume is a random variable because each one of those rocks has a volume. So anyway, those are random variables. And it turns out that this formula is an inner product. So what? So something involving statistics satisfies an abstract property. Right? Who cares that something in statistics satisfies an abstract property? Well, here's the thing. Here's why we care. This statistics relation that I deride the pointlessness of it satisfying this abstract property of being an inner product. You can relate these other statistical notions to formulas that involve that inner product. In particular, one of them, correlation, relates to angle. And that's weird. Right? That's super weird. And again, let's go back to the bucket of rocks example. So here's a bucket of rocks, a bunch of, let's say, pebbles in there. Right? Zillions of pebbles. Each pebble has a mass. Each pebble has a volume. Pebbles with bigger mass tend to have more volume, but that's not a perfect relationship, right? Sometimes there's a pebble that has a lot of mass, but it's really dense. It's got a lump of iron in it, maybe. And so it's got a low volume but a high mass, right? These counter examples. Maybe there's one that's got an air hole in it, whatever. Right? So we would say that mass and volume correlate. There's a high correlation, positive correlation. But they're not exactly the same, and there's not a perfect linear relationship. Okay, so I'm saying here that relates geometrically to a notion of angle. So random variables, again, I'm claiming we have an inner product space of random variables, and completely non-physical though it is to think about, I can think of the random variable called mass as being a vector in that inner product space. I can think of the random variable called volume as another vector. And I can think of them as having an angle between them. Not surprisingly, because they correlate, right, you would want to think of those as having an angle between them that is highly acute. Right? And just think about how cosines work, right? If you have a correlation that's high, near 1, what angle has a cosine that is near 1? Well, it'd be a small angle. Right? Okay. So thinking of correlation as something geometric is I'm going to call it unexpected, and here's why it's valuable. There's an amazing property about correlations. It's very counterintuitive. Suppose you have a couple of random variables that are positively correlated, and let's stick with my bucket of rocks. Mass and volume, positively correlated. The ones with the big pebbles way more, right? I mean, general rule, all exceptions granted. More mass, more volume. most of the time. Now let's suppose that you can think of another random variable, z, and suppose that's positively correlated with y. So, okay, mass and volume are positively correlated. Volume and I'll call radius. Let's say diameter. Let's say diameter. It's easier to describe. Diameter is like, what's the biggest distance? What's the longest? If you were to try to arrange that pebble so that it's as wide as possible, how wide is it? Right? Let's call that the diameter. Well, volume and diameter positively correlated, right? I mean, big volume pebbles tend to be wider, and wider pebbles tend to be more volume. I mean, all exceptions granted, you could have a weird pebble that's a long, skinny little needle shape or something, right? But that's unusual. So now again, think about the rocks. More mass tends to have more volume. More volume tends to have more diameter. Wouldn't you think? I mean, I find this highly satisfying to believe that rocks that have more mass, shouldn't they also, as a rule, more often than not, all exceptions granted, shouldn't they also have more width? More mass, more width? Doesn't that seem kind of plausible? I mean, if X and Y are positively correlated, X and Y tend to go hand in hand, Y and Z tend to go hand in hand, shouldn't X and Z kind of go hand in hand? Try it with a friend, two friends, right? If I'm holding your hand, you're holding my hand, and three of us are walking down. It's hard for these two people to be going opposite direction, right? And yet that's the reality here. This is a super weird fact, super inconsistent with intuition about how stuff tends to work, right? We feel like if X and Y are positively correlated, if Y and Z are positively correlated, well, for crying out loud, shouldn't X and Z be positively correlated? And it's stunning and frustrating that they're not necessarily. They might be negatively correlated. Now, counterintuitive though this is, let me show you why then it's valuable to think about this as an inner product space. Right? If you're thinking about statistics from the point of view of examples like pebbles in a bucket, you're going to be limited. But let's remind ourselves that correlation, a positive correlation, all that really means is an acute angle. So now forget about pebbles. Let's just think about geometry. If you have two vectors with an acute angle between them, and then the second one has an acute angle to a third vector, do the first and the third vector have to have an acute angle between them? Well, no, of course not. That's ridiculous. Look, this angle is acute, and this angle is acute. There's no reason to believe that this angle should have to be acute. In fact, here's an easy counterexample. Look, there you go. Two acute angles do not add up to an acute angle, always. Sometimes acute plus acute adds up to obtuse. So this is geometrically obvious, right? Highly believable. And that is the point of view. I mean, so this very satisfying point of view relates by way of the inner product construction to this otherwise mystery of how could correlations not sort of transfer like this. Right? You'd really think that there would be some sort of a transitivity of correlation. So anyway, I credit the inner product as being the thing that allows us to get some intuitive understanding of this otherwise mystery. Okay, so again, if you've taken a stat class, think about how this might track with things that you might have seen there. If you have not, be on the lookout for something like this. And this is a pretty good place to stop. We'll call it a day right here. See y'all later. Have a good Wednesday.